All right, so okay. So the next thing we will do, we will combine compactness with continuity and see what we get. Uh, Continuity and compactness. Okay. The first observation is this. The image of a compact subset under a continuous function is also compact. So let f, let's say from x y from x to y be a continuous function of metric spaces. If E is a compact subset, then so is f of x. Okay, so if you take a compact subset in x, its image in y is also a compact subset. And here is the proof. Well, we may use any equivalent characterization of compactness. What was that? We may use open covers, we may use sequences, and we may use also pre-compactness and so on. Let me use here well, sequential compactness, or let's use the definition. Okay, both are okay. Okay, let me use one of them and leave the other one to you as an exercise. Let me use the sequential compactness definition. Okay, so take any sequence yn in okay, I should say f of e, sequence in f of e, right? The proposition says the following: if you take a compact subset of x, then its image is a compact subset of y. Now I want to show that f of e is compact, and to show that I take any sequence in f of e, and I want to show that this sequence has a convergent subsequence. So I must show yn has a convergent subsequence. How can I prove this? Well, yn is in f of e. Since yn is in f of e, there is some xn in e, sorry, so that f of xn is equal to yn, right? In particular, this xn, so xn's form a sequence, is a sequence in E, which is compact, which is a compact subset or subspace. Well, since it is compact, any sequence in that space has a convergent subsequence. So xn has a convergent subsequence. Say x kn, okay, kn with limit xkn equals x0. So this sequence xn has a subsequence xkn. It is convergent. Of course, both xkn and its limit point is in e. But I know that f is continuous. Now, since f is continuous, f of x0, let's say y0, I define y0 as the image of x0. This is just f of limit of xkn, because x0 is this thing. And since f is continuous, I can take this limit outside limit of f of xkn. So this is just limit of ykn. So what I obtained is then the corresponding subsequence in f of e, ykn, has limit equals y0. Okay, where y0 is in f of e, since x0 is in e. So we have obtained a subsequence of yn which is convergent, right? So I started with this sequence, take any sequence, and I must show that yn has a convergent subsequence, and here is the convergent subsequence. Okay, so this finishes the proof. Okay, there is an alternative proof. I will leave the details to you, but here is what you do to show that f of e is compact. Take any open cover, let's say O alpha for f of e. Okay, so I have this. E is a subset of this O alphas. Alpha is in some index set, and these are just open for all alpha here. So I have a collection of open sets covering E, and I want to show that finitely many of these O alphas is enough to cover f of E. How can we do this? Well, f is continuous, therefore inverse image of any open set is open. Now take inverse image, then f of E, inverse image of E, will be contained in the inverse image of this union, but this is equal to this gadget. And where each f inverse of alpha is open in X, since f is continuous. And clearly, oh, okay, I have to be a little bit more careful. I take an open cover for f of e, sorry, yeah. And when I take inverse image, so, okay, I should be more careful. Now, E is what? E is inside of f inverse of f of E, right? And f of E is contained here. Okay, so E is contained in the inverse image of f of E because E is mapped into f of E, and f of E is contained in this union, and this union, the preimage of this union is this. Therefore, I obtain an open cover for E. Okay, uh, so uh, so that this collection F inverse of O alphas is an open cover for E, and then you use compactness of E. Okay, finitely many of these will cover E, and then you will send them to back. You will send them back to Y via F, and they will cover F of E. Okay, so the rest I will leave rest as an exercise. Okay. All right. So what we have proved is that if you have a continuous map, then image of any compact set is compact. Okay. This is a very nice, actually, consequence. So called homeomorphism theorem. Homeomorphism theorem. It gives us the following. Let f be a continuous uh, bijection. So it is one-to-one, onto, and continuous. If therefore f inverse exists, okay, since it's a bijection, f inverse exists, but we are not sure whether f inverse is continuous. The theorem is this: if X is compact, then F is a homeomorphism. Before the proof, let me give you the following remark. You know, this is certainly not true if you drop this assumption of compactness. For example, consider this example. Let X be the following metric space. So I take real line, but here I put the discrete metric. Okay, and Y are with the absolute value metric, the usual metric on R. But here I have discrete metric, and let F be this function, f of x equals x for all x in R. So this is just the identity function. Okay. F is clearly a bijection because it is the identity function. F is clearly a bijection. And it is continuous because here x is the x has the discrete metric. Therefore, any subset of x is open, right? So to check continuity, what I have to do, I have to take a closed open set and take its inverse image. Whatever the inverse image, it's an open subset of x. Therefore, it is open. Since x has the discrete metric, any subset of x is open, and thus f is continuous. However, if you look at the other way around, however, f inverse, this time from y to x, is not continuous. Why is that? Because look at this set u, which is 0 here and 1 here. Okay, this set in x is open in x because x has the discrete topology, therefore any subset is open. But let me call this function g inverse, but g inverse of u, what is g inverse of u? Well, it is the f is the identity function, f inverse is also the identity function, g inverse of u is just u, is not open in y, which is the metric space of real numbers with the absolute value metric, right? This is not open. So this result is not always true, right? So I have a continuous bijection and its inverse is not continuous. The reason here is that, of course, x, the metric space x, is not compact. This metric space is not compact with the discrete metric. Okay. You can actually do this not only for R, actually you may put here any metric space, okay, any metric space or any subset of R. Instead of R, you could just write here also, for example, the interval 0, 1. Okay. 0, 1 here, 0, 1 here. You could do this also, but let me keep it now here. All right. Now, why this theorem holds? Proof of the theorem. So f from x to y, continuous bijection, and x is compact. Okay, x is compact. Let g be the inverse of x, inverse of be the inverse function f inverse. Okay, so we must show to show that f is a homeomorphism, g is continuous. How can we show G is continuous? Well, take any closed set A in X. Okay. Remember equivalent forms of continuity. One of them was epsilon delta definition. The other one was uh, inverse image of any open set is must be open, or inverse image of any closed set must be closed. So I use that characterization of continuity. I take a closed set and we must show that G inverse of A is closed. But then what is G inverse of A? G inverse of A is what? Well, F is a bijection and uh, G is just F inverse, the inverse function. So when you take G inverse, okay, this is the set of points in Y which are mapped to uh, A via G, but this is nothing but, right, this is just F of A. Wait a minute. Inverse image of okay, so this is F inverse and then inverse image of A. This is just ne olacak bu? Inverse image of, okay, this is just A. Okay, let me write it this way. So G is a function from Y to X. Okay, A is a subset here. G inverse of A is the set of all points in Y such that G inverse of Y, no, G of Y is in A, right? G of Y is in A. So this means what? G inverse of A is the set of points here so that their images lies in A. So this is nothing but, okay, so this is, let's say, X, okay. So this means f of x is equal, f of x is in this, so this is just f of a, right? X is gy, therefore f of x, f of gy, so this is just y because f and g are inverse of each other. So this is a set of all y's, and y is just f of x. So this is just f of a. And f of a, uh, since a is a closed set in X, uh, is a closed subset, and thus A is compact. But f is continuous since f is continuous, f of a is compact. Image of a compact set is compact, but we know that any compact subset is closed. Hence, f of a, which is just G inverse of a, is a maybe I write it this way: f inverse of G inverse of a, f of a, is a closed subset of y. So what I did is then is the following: to show that f is G is continuous, I take a closed subset here. I want to show that this map is continuous. I take a closed set here, and I show that its inverse image is a closed subset of y. Therefore, G is continuous. So that G is continuous. So I have what? F is a continuous function. It's a bijection, and its inverse is also continuous. Thus, F is a homeomorphism. Okay, that's a very important result. Okay, all right. Do you have any questions so far? So, if you are on a compact space, and if you have a function onto some other metric space, and if your function is one-to-one and continuous, then that function is necessarily a homeomorphism. Okay, all right. Now the next thing we will do is a theorem from actually first year calculus course. Okay, on a compact closed and bounded set, any continuous function has a maximum and minimum. We will prove the generalization of this to metric spaces. Here is the theorem, minimum maximum theorem, minimum maximum theorem. Okay, here is the result. Let XD be a compact metric space. And f from xt into real line, okay, be a continuous function. Then this function has a maximum and minimum. Then there are points x, let's say max, and x min in x, so that f takes maximum value at this point and minimum value at this point. So this is how we formulate this. X min is less than or equal to f of x, and this is less than f x max for all x in x. Therefore, this is the minimum value of f, and this is the maximal value of f. Okay, and the proof is very, again, simple. How? Well, f of x is a it's a compact metric space, and f is continuous. Therefore, the image is a compact subset. Is a compact subset of real line with the absolute value metric. In particular, f of x is closed and bounded. Well, since it is bounded, it has max, supremum and infimum. In part, so hence supremum of f of x and infimum of f of x exist because it is bounded. Moreover, since this is a closed set, its supremum belongs to the set, right? If you have a closed and bounded set, then its supremum is the limit of a sequence in f of x. Therefore, supremum belongs to closure of f of x, but f of x is already closed, right? Right. So if supremum is here, let's say, and this is, let's say, f of x, there's a sequence in f of x converging to the supremum, but limit of a sequence in f of x belongs to the closure of the set, but since f of x is closed, this closure is f of x. Okay, so moreover, since f of x is closed, both supremum of this set and infimum of this set belongs to f of x. Well, this supremum, whatever that is, so let's say M be the supremum of this set, okay? Supremum of this set. And this belongs to f of x. This implies there is some point here. Let me call it x max, so that f of x max is equal to m, and let's say infimum of f of x is little m, and we know that it belongs to this image set. Therefore, there exists a point, let me call x min in x, so that f x min is equal to small m. Well, now if x is in x, then of course f of x is less than the supremum, because f of x belongs to this set, and certainly it is less than the supremum and greater than maximum. This is just x min, f of x min, and this is just f of x max. And this finishes the proof, okay? So as a corollary, if let's say f from AB into R is a continuous function, where we use where both have the absolute value metric, So on this metric space I use the absolute value metric, and on R also I use the absolute value metric. Then F has a maximum and minimum. Why is that? Proof. Well, AB is a closed and bounded subset of R. Hence, AB is compact. And since it is compact, a continuous function on a compact set has a maximum and minimum. So we are done by the previous theorem. METU. What was it? Yes, maximum minimum theorem. By the previous max min theorem. Okay. Any questions? Right. We already knew this from first year calculus course, but maybe you might have seen it in advanced calculus. But here we just see that this result holds in much more generality. Okay, for any compact metric space, the same thing holds. Okay. Another corollary of this is the following. If XD is a compact metric space, okay, then CX is a closed subset of BX. So let me explain what these are. Remember, BX is the set of bounded functions, right? So this is the set of F is bounded, and CX is F is continuous. In general, a continuous function need not to be bounded, right? Remember the identity function from the real line to itself. X goes to X. It's a clearly continuous function, but the function f of x equals x is not bounded because it takes arbitrarily large values. However, if your domain metric space is compact, then we know that any continuous function is what? Has a maximum and minimum. Therefore, a continuous function cannot take arbitrarily large values. It is bounded by its maximum and minimum, right? Here, of course, I am using supremum metric. So note that since X is compact, any continuous function f from x to r is bounded actually by its extreme values, right? Extreme values. So Cx is a subset of Bx. Any continuous function is bounded. But we claim something more than that. We claim that this is a closed subset. Closedness comes from the following. Well, we proved earlier that if you have a sequence of continuous functions, and if this sequence converges uniform, if this sequence is convergent, so if I have a sequence of functions converging uniformly, then the limiting function is also continuous, right? Recall for the second statement, recall that we have proved that if Fn is a sequence of continuous functions on X, and limit of Fn equals to F0, of course here I am using supremum metric, so D submetric for functions, then the limiting function F0 is also continuous. So this means what? If I have a sequence here, and if it is convergent, then the limit belongs to that subset, because limit is also continuous. Therefore, closure of Cx is equal to Cx. In particular, closure of this is equal is what? Is Cx. So that Cx is a closed subset. In particular, of course, Cx is complete because Bx was complete in the submetric, and it's a closed subset. Therefore, Cx is also complete. Okay. Maybe I should say this. Is a closed subset of Bx in particular. Okay. In particular, Cx is complete. So the metric space of continuous functions is a complete space. Of course, in the supremum metric. Okay. I am almost done. There is one little thing I have to do. I'll do it Thursday. I'll talk about Lebesgue numbers and uniform continuity. But let me just do it on Thursday. Okay, let me stop here.